Okay, welcome back. We are going to be looking at Newton's third law of motion. Okay, so the basic idea here is that for every action, there is an equal and opposite reaction. Okay, and what do I mean here? That just means that for every action, there is going to be some other force that is equal in magnitude and opposite in direction to that first force. Okay. And just noting what a normal force is real quick, that is the force that is perpendicular to the surface of contact between um, some mass and its support. Okay. So let me go ahead and give you guys an example. So we have a person sitting here on a chair. Okay. Now that chair is going to be our surface of contact, okay? And that is going to be between the mass, which is the person, okay? And the support being the chair, okay? So this is our surface here, okay? And we have the force due to gravity, okay, of course. And that is going to be our first force here. And then we have an opposite force that is called our normal force, okay, in our perpendicular direction. Okay, so it's going to be completely opposite, but with the same magnitude. Okay, and that normal force is being exerted by the chair or that support onto our mass, which is the girl. Okay, so that is the basic idea. Now I want to talk about another type of force real quick, is called tension, okay? And that is a force that is along some medium, like this rope here, okay? And tension is defined as the weight of the supported mass, okay? So if we have some mass that is being supported by a rope or a cable, some kind of medium, okay? Our tension can be calculated as our weight, okay? And that weight is our force, which is going to be our mass times gravity. Okay, so our tension is going to be our mass, and that is going to be multiplied by our gravity. And again, that equals our tension. Okay, and here is our free body diagram, so we don't have to draw the weight out, but you can see that it's the same idea. Okay. Now, just to get you guys to understand the third law, okay, I have a couple examples here. So here I have a rocket that is spitting out fuel, okay, and that would be its action. Okay, now its reaction is going to be the lifting off. Okay, so we have two forces in play. We have our action and reaction forces. Okay, same thing here. We have a car, someone driving a car. We have a force that's exerted by the tires to push against the ground. And then we have a force exerted on the tires by the ground. And with those two forces acting in play, okay, the car is able to move forward. Okay, so again, that comes back to the whole, we need to understand physics in order to kind of progress, and this is an example here. Okay, now I have three different scenarios here. Okay, I have scenario A, B, and C, and I want you guys to kind of think about what law can be represented in these three scenarios. Okay, and then I will kind of go through them, so if you want to pause the video and think about them for a second, that would be good. Okay, if not, I'll come back in just a second here and talk about each one of these scenarios. Okay. Okay, so I will go ahead and continue. So when we're looking at scenario A here, we have a woman standing next to a full basket. Okay, she's not touching the basket, she's just standing next to it. Okay. What I am trying to go for here as to which law is that for every, the basket that is full is not going to go anywhere, right? It's just kind of sitting there and she's standing next to it. So there's no forces being acted on this cart. But as soon as she does act on it, okay, as soon as there is a force, then the cart will move. Okay, so that is the idea of Newton's first law of motion. Okay, so first law states an object in motion will stay in motion, an object at rest will stay at rest, and that's exactly what we see here. The shopping cart is not going anywhere, okay? Now for the second scenario, scenario B, okay? Let me kind of put you guys what I'm kind of seeing here. I have two guys and they are both pushing carts, okay? One of the carts is empty and one of them is full, okay? So if I wanted to know what type of forces these guys would need to exert on these carts to get them to move, okay, I would be using Newton's second law of motion. Okay, so remember that a force is equal to a mass times an acceleration. Okay, so if I want to know how much force each of these guys would have to use to move these carts, okay, I would need to know their masses, which we could find, okay, and their accelerations, okay? So by doing that, we can use Newton's second law, okay? Now, our third scenario here, scenario C, we have a guy actively pushing a cart. Okay, and there's only one law left, so we can probably, with an educated guess, say that this is going to be our third law of motion. Okay, and again, that states for every action, or the guy pushing on the cart, there's an equal and opposite reaction, the cart pushing back on him. Okay, so hopefully this gives you a little bit of insight, okay, to this. Now I wanted to give you guys just a quick little list of 4 basic forces, types of forces, okay, that we see. And the first one being gravitational. Of course, that one we see every day, okay. You know, an apple will fall, right? That is law of gravity or force of gravity, okay. We have electromagnetic. We have a weak nuclear force and a strong nuclear force, okay? And this gives you quite a bit of information, okay? The main one that I want you guys to understand, though, for this semester is the gravitational force, okay? Know that it is only an attractive force, okay? So it doesn't repulse anything, it's only attracting, right? We're being pulled down to the earth, we're not being pushed away from it, right? So that's basically it, but I just wanted to kind of give you guys a bit of, you know, other examples, okay, that what we see, okay? All right, so for this last slide, before we get into all of the examples, I want to give you guys a little bit of a problem-solving strategy. Okay, so we have here somebody pulling down on a rope, okay? So this is going to be our first step in our problem-solving strategy, which would be to sketch the situation. Okay, so what are we looking at? The second one would be to identify our forces. So what is going on here? We have a rope, right? And there has to be some tension because he's pulling on it. So there is a tension from the person on the rope, okay? Then we have the weight of the person, okay? And we have some other force here, okay? I'll talk about that in a second. So our next thing would be defining our system of interest. Again, that is going to be our guy here. That is our system of interest, okay? Now this is our free body diagram where we have our tension, okay, and our weight of the person. So that is our simple free body diagram, okay? And then our last step is going to be to add the forces together, okay? So typically it would be like F1 plus F2, okay, blah, blah, blah. And as it states here, these forces must equal or be equal and opposite, okay, since the net external force is 0. So their addition must be equal to 0. Or our first force must be equal and opposite. Okay, so that's what we have here. Our tension is going to be equal and opposite to our weight. Okay, and these should all have vectors because these are all vectors, right? They all have direction as well as magnitude. Okay, so that's the basic idea that we have here. All right, so in the next video, I will go over in more detail how to do these problems. Okay, so this I know was pretty quick, but we will go into more depth in the next video of how to do these problems, how to approach them, and your free body diagrams, all that good stuff, okay? All right.